Okay, so let's talk about if it's a weak base and a weak acid. This one is the most difficult. It's not the most difficult in the sense of like the math is crazy hard. It's difficult because there's no way to really predict it in a general setting. So we kind of have to figure it out case by case. And so the only way we can really do this is we have to kind of look at some qualitative results, look at some data, and then just compare. So say I wanted to react to this guy, NH4F. Okay? So this is my salt, NH4F is my salt. Okay? So this is the salt, and I'm reacting with water, and I don't know which one is going to be more prevalent. Was it my NH4 plus ion or my F minus ion? Which one of these guys is the one that's going to be the determining ion? Okay, so remember in our last one that we did here, the determining ion, this guy, came from my weak base. So it was a weak base, the ion is acidic, and that's why it ends up being acidic. But I don't know if my ion, which one of my ions, are going to be the determining one, because they're both weak. So what I have to do is I have to look up what is the Ka and the Kb for my ions. So for NH4 plus, this is going to be an acidic ion, so I want the Ka. Then I get F minus, because this is a basic ion, I get the Kb. So I find those values. I find the Ka, I find the Kb. And then I need to compare them. In this case, the Ka for my weak acid is greater than the Kb for my weak base. I compare the numbers, 10 to the negative 10, 10 to the negative 11. So the Ka is a bigger number than the Kb. So if that number is a larger number, that means that this guy, the NH4 plus, which is the ammonium ion, that reaction is more favorable. Okay? So if he's got the reaction that's more favorable, then the Ka is what I would go with, and whichever one we go with is what the solution will be, which would be acidic. So it just depends on which one's stronger. You need the K's and you compare the K's. And the K's you would just get from a book or a chart. Okay? So this one is complicated, but there's no math really other than comparing two things, so it's easier from a standpoint of problems for you guys. All right, so let's summarize all of our choices. We have strong acid, strong base. So if I have strong acid, strong base, I get my salt solution, and we said these cancel each other out because strong cancel each other out, so they neutralize and my pH is 7. All right, strong, weak. The strong one cancels this one out, so it overcomes it. So what's left is acidic. So I'm going to have an acidic solution. And the pH would be what for acidic? Less than 7. All right, now it's the flip. Weak acid, strong base. The strong acid is going to, the strong base is going to overcome the weak acid. So I'm going to have just the basic solution left. And that means the pH is greater than 7. Okay? If I have weak, I don't know who's overcoming who. I have to look at the K's. So whichever K is the larger K, that's the one that's going to overcome the other guy. So here, my pH is kind of, I don't know. It depends. So just have to know that whichever one has the stronger K, that's the one that's going to overcome. Okay? All right, so let's move on. So that's salts. We only have 2 more things that we need to talk about in this chapter, and we're going to be done. So it'll be a short lecture day. So the next thing we want to talk about is polyprotic acids. Okay, so let's look at the name. So polyprotic acids, so they're acids. Poly means more than one. Protic is short for proton, and in this chapter it's an H+. So what this means is that these are acids that can donate more than one H+. Now remember we talked about the conjugates. A conjugate acid, conjugate base is only one H plus moving. We're not talking about conjugates. We're just talking about how many times can an acid just act like an acid. Okay? So for example, HCl has only one H. So it can only donate one H plus. So it's a monoprotic. And it can only donate one. H2S can donate two. This is a diprotic acid. H3O4 can donate three. This is triprotic. This one's two. Another diprotic. This one's got an H here and an H here, so that's two. Another diprotic. Now here, you might say, well, he's got 5 and then 8, so that's 8. It has to be hydrogens that are kind of on the outside that are able to pop off, okay? And so this guy, these hydrogens, this is a carboxylic acid right here, so these hydrogens can pop off, these can't. So he's triprotic. We actually had a problem. Let's see if I can find it real quick. Where was it? I think it was our first one that we did. Here we go. See? This was lactic acid. I didn't give you the formula, but I told you it was monoprotic. I was telling you it was only going to do one hydrogen. If it does more than one hydrogen, you have to actually calculate the pH every single time it removes one. So you actually have to do this math for as many protons that are going to be removed. So this was diprotic, you would have had to do this twice. Okay? If this was triprotic, you would have had to do this math 3 times. So when I'm telling you it's monoprotic, then I'm giving you a hint it's only going to give up one. Okay? Now if I ask you, like on a quiz or something, how many it's going to give up, it's going to be the simpler guys. Or if I do give you something, it'll be like this, where literally you can just count the hydrogens. Okay? I won't give you anything too challenging. So, for each H+, every time it gives up an H+, it's going to have its own Ka. So every Ka it gives up an H+, that's the Ka. So you might have so for this guy, he has 3 Kas. Ka1, Ka2, Ka3. Ka for the first time, the second time, and the third time. Okay? The first proton is going to be the easiest to remove. So removing that first H is always going to be the easiest. Okay? So it's going to have a pretty high Ka. Okay? The second is going to be harder. So remember, Ka is how easy it's going to remove. So that means that Ka1 is going to be higher than Ka2. Because Ka is how much does it want to be an acid. So if it's got a really high Ka, it's a strong acid, meaning it really wants to give up protons. So the first one, it's easier to give up the first one than the second one. All right, so let's look at this. Phosphoric acid, he has 3 H's. So how many acidic protons does he have? How many can he give up? 3. Okay, so let's look at this. Here's how we would look at writing this. So here's my acid, reacts with water. He's going to give up the H+ to the water, so he's going to have 1 less. The water will have another one, because remember partners. And I would be able to do the Ka. Now, the second time, it doesn't come from here. It comes from what's left over. So that guy, what was left over, now gives up another H+. So now he has another hydrogen less, and then the water gains the H+. And now I have his first Ka, and now I have his second Ka. Then what's left comes down here. He's going to give up the H+ to the water, so now he has no H's left, and then the water gained it. So now I have his third Ka. Okay? You won't have to write these. I just want you to see what's happening. You can't do all 3 in one fatal swoop. What happens is the phosphoric acid gives up the first one, then he's going to give up the second one, then he's going to give up the third one. So you have to do it by steps. Okay, so let's look at these Ks. This one's 10 to the -3, so pretty high. 10 to the -8, 10 to the -13. So as I go from my first to my second to my third, as I go and remove more, so as I remove my H pluses, my Ka value is starting to get smaller and smaller. And so if the Ka gets smaller, that's because it's really hard to remove, it's going to be hard to remove my H plus. So like I said, as I'm going from first to second to third, it's harder to remove the H plus. That's why my K gets a lot smaller. Because the K, the bigger the K, the stronger the acid, the more it wants to give up the H plus. Okay? Alright, I'm just going to go ahead and put this one in this lecture since this one isn't too long so far. The last thing we want to talk about is another definition for how to define an acid and a base. So, I know, you're thinking, what, another one? So you already know the Arrhenius definition. Okay, that's who produces H plus, who produces OH minus, and you know the Bronsted-Lowry. Acids are proton donors, bases are proton acceptors. Okay, so now we need a new definition. And the reason we need a new definition is because when you start to move to organic chemistry, or if you get up into the higher levels in inorganic chemistry, some things can be acidic or basic that are a little different than what we're used to seeing. So we need a third definition to kind of encompass our exceptional, odd-behaving guys that you wouldn't really see in a general chemistry course. Okay, so I'm going to introduce these to you because if you ever read about, an article, a scientific article, and you hear this, you might be like, I never learned these. So this is just like a little introduction about these. So you're just gonna have to know the definitions and that's about it. All right, so let's talk about Lewis acids and bases. This is the most general definition. So Bronsted and then Arrhenius, and now we got Lewis. So Lewis acid and Lewis bases. We're gonna still talk about accepting and donating, but instead of transferring an H plus from one to the other, we're gonna be talking about a pair of electrons. Okay, so we're gonna be going and moving a pair of electrons to form a bond. So this looks very different because we're not talking about any H pluses and we're actually combining things. So a Lewis acid accepts, so you can think Lewis acid accepts, a Lewis base donates. Lewis base donates. So just like law, if you want, law and not lad. So don't flip these because then it would make LAD. So it's not, this is wrong. It's not lad, it's law. So that's how you can think about it. Okay? So let's look. So here's my acid. It's an electron pair acceptor. The base is an electron pair donor. So what happens is he donates these electrons, and instead of just giving them to him, so he becomes a cation and he becomes an anion, we actually make a coordinate covalent bond. Okay? So we're gonna make a new type of bond that we have not heard of before. Now, we've heard of covalent, because remember covalent was sharing electrons? We know ionic bonding, covalent bonding. A coordinate covalent is where it's sharing, but it was donated, the electrons were donated by one atom, the same atom. So in our covalent, I shared, somebody else shared, we put them in the middle, and that's what happens. Coordinate covalent is we're sharing one thing. I put both electrons in and we're sharing my pair of electrons. All right, so let's look. If I gave you this and I asked you who's the Lewis acid and who's the Lewis base. So here's my reaction. And we want to know, so it kind of helps to draw out the Lewis structures, hence the name Lewis acid base, kind of helps you, same guy. So if I'm going to be donating an electron pair, I got to have an electron pair to donate. And it's going to be on whoever's making the bond. So let's look. So this bond is this bond. Okay? And this bond is this bond. So the new bond is here. So the new bond's between the O and the H. Okay? So what I got to figure out is who's giving what. He has no electrons. So it's got to be these electrons coming here to make the bond. So if he's giving the electrons, he's the base. If he's accepting, he's the acid. All right, let's do another one. This is this. Let's find the new bond. So my new bond is this one. I'm not sick, I promise. My mouth is just dry. All right, so if this is the new bond, then it's between the B and the N. So I need to see who has an electrons. Well, N has the electron, so he's going to give it to the B, the boron. So he's going to be the base. He's going to be the acid. But I only know that if I draw my Lewis structure out. Okay, so that's one way for us to figure this out, is who has the electrons. Another way that we can look at this is that we can figure it out based on if there's a cation or anion or those kind of things. So metal anions, or metal ions, so here's a metal, here's a silver, he's got a plus, he's a metal ion. These guys are going to act as Lewis. What do you think? If he's a cation, do you think he's going to want to gain electrons or donate? So if I'm already positive, I don't want to donate electrons because that means I have less. So if I'm positive, that means I want to accept electrons. So he's going to be, they're going to be metal acids. So they're going to be, so if it's a metal here with a charge, metal cation, he's going to want to be an acid because he's missing electrons already. He's got spaces for those electrons. And so here, he's got the electrons. He's going to give him the electrons, so he's the base, he's the acid, and we make this bond right here. And because there's two of them, he could do it twice. Okay? Now, let's talk about OH minuses. So these are hydroxides. Let's think about what we think he might do. So he's a negative, so he has extra electrons. So if I have extra electrons, do I want more, or am I okay with giving them up? I'm okay with donating them. So if I'm okay with giving them up, then I'm going to be a Lewis base. So hydroxide ions are going to be Lewis bases because they have this oxygen right here. He's got a bunch of electrons. Bunch of electrons that he can do, so he can easily donate a pair of those and be fine. Okay, so that's a metal by himself. This is a hydroxide by itself. Now let's talk about if it's a metal hydroxide. Metal hydroxides are where it's a compound that has the metal and the hydroxide together. So here it's aluminum hydroxide. So because it has the metal and the hydroxide, the metal wants to be the acid, the hydroxide wants to be the base. So they're kind of fighting to see which one they're going to be. So they are going to end up being amphoteric. What's something else that we talked about that's amphoteric? Water. Okay? Now, water's a little different in the sense because that's talking about protons, so it's amphiprotic. But the idea of it being able to act as an acid or a base, that's what we're going to talk about here. So water can act like an acid or a base, and metal hydroxides can act like a water or a base. Just this A word is a little different. Okay? So hydroxides, they can react with acids and bases and be whatever they need. Okay? So here, this hydroxide is going to react with a OH minus. So if it's an OH minus, we said hydroxides, these guys like to be the base. So if hydroxides want to be the base, then that means he's got to be the acid. So the electrons that are chilling here are going to come over. Whoops. Let's draw more accurately. Come to the Al. And then we have 4 hydroxides attached. Okay, let's look here. He is a plus. Now, we only talked about metal ions, but we can kind of think about this. If he's a plus, is he going to gain or lose electrons? Like, which one would he probably want to be more if he's a cation? Yeah, so he would rather be the acid. So if he's the acid, then that means that he's gonna be the base. Now in this case, it's gonna be a little different. Instead of it actually making a bond, they end up acting more like a Bronson-Lowry base. And so they don't create a new bond, like here they're added together. They're actually gonna give up and then break apart. There's a lot going on, okay? You don't have to know all that. All you have to be able to do is figure out that this would have been the acid, this would have been the base. Exactly which way it's gonna react and all that, that's fine. You take higher level chemistry classes, we'll get into this a lot more. Especially organic, they get into acid bases a lot. All right, let's talk about the last one. What if I have non-metal oxides? So this is gonna be something with a bunch of oxygens and a non-metal, so like sulfur or carbon. So here, you're gonna have the non-metal and then the oxygens are gonna have a lot of electrons. Okay, so you might think because the oxygens have a lot of electrons, that it's gonna donate all those electrons. Well, it's not actually what happens, okay? These are actually going to act as acids because remember, it's not the outside guy, it's the middle guy. It's always our central atom that's doing everything, okay? So what happens here is we can look, so the oxygen attracts the electrons from multiple bonds, and so it leaves our non-metal electron efficient. So our non-metal can have some more. So here's an OH minus. Remember I talked about these guys like to be bases. So he's going to attack the carbon. The carbon doesn't have any electrons, so that's one thing. Carbon doesn't have any electrons, so you can't really give them. And also he's electron deficient. Okay? So remember, because the oxygen has a lot of electrons, and we talked about electronegativity, these electrons in this bond are being pulled this way. These are being pulled this way. So you get a partial negative, partial positive. So he doesn't have electrons on him, and he actually has a partial positive. So he's really wanting to be an acid. Same for if I have a sulfur. There's an electrons here. Ooh, way too many electrons. I drew way too many on this one too. My bad. Sorry. Fix that. But he's got all of them. So oxygen's more electronegative, pulls this way, so you get your partial negatives and your partial positive. So sulfur, carbon, so my non-metal is electron deficient. So he's definitely not going to be the base. He's not going to be the donor. Hydroxide, we said, wants to be, so he's going to donate these electrons. But carbon can only have 4 bonds. So what happens is these electrons, either side, are going to move here. So this here, this creates my new bond, which is this bond. And then these electrons in the bond now become lone pairs, which will be these guys. Okay? So, let's review. Lewis acid accepts, Lewis base donates. Metal ions want to be acids, hydroxide ions want to be bases. Metal hydroxides could be either or, depending on who they're with. And non-metal oxides like to be acids. So that covers everything from chapter 16. So we have finished all of chapter 16. Okay, so I'm actually gonna, so that's our last lecture for this semester. I'm gonna post chapter 18 on Miles Must Say. There's not gonna be anything that you have to do with it graded wise for my class. But here's what I'm gonna tell you. If you wanna take a chem elective this upcoming year, or at any point, what you need to do is you need to go through the chapter 18 material that I post, and you're gonna have to work the problems and learn the material. Now I'm gonna send this all out in an email this summer. You'll get all this information, so don't feel, and you have all summer to do it. So you don't have to do it by the end of the semester. So I'm gonna send you chapter 18 notes. I'll send you some lecture videos because Chem 2 has already done it. So we actually have some videos for 18. So you're gonna get videos for 18. You're gonna get all of that, okay? The videos for 18 will not be from me. I think they'll be from Dr. Stover, and you'll have her slides, so there'll be a little difference there. But you're gonna have filled in slides and everything like that. And so just review it try to do the problems, ask me questions if you have any, but you're gonna wanna know that chapter 18 material for any of the electives you take. It's gonna be a requirement that you've completed this before we let you enroll also, okay? So just start thinking about it, and sometime in May or so, we're gonna be sending out, you know, the requirements for that. All right, hope you've enjoyed the semester. I've enjoyed teaching you, and even though this is your last lecture for Chem, you'll notice on Milestone Say there's gonna be one more lecture, and so that's just like a little fun bonus lecture, so you should check that out, especially if you're just in a sad mood. You should check it out, trust me. All right, well, have a good one, and if you need anything over the summer or anything, you know, in the next couple of weeks or whatever, just know, like, I'm here for you. And a lot of you still kind of live a little closer, or maybe you live near my mom or whatever. And so if you need something, I'll figure out how to get it to you or to help you or whatever. So just know that even though you're not here, you know, we still love you, we still care about you, and we still want to do things for you and help you out. So if you need anything, just let me know. Don't be shy. Bye, guys.